Hello, this lecture is going to be over the first part of Chapter 2, Discovering the Universe for Yourself. What we're going to focus on in this actual lecture is the motions of the Earth and specifically on constellations. What I'll do is I'll break this up into multiple videos so that they're shorter in duration, and so you can kind of pick out exactly which part that you want to see and which part that you want to, focus on. Okay, again, just a kind of a review of the Earth's motions. You can see that the Earth rotates on its axis and we revolve around the sun and that the solar system is moving amongst the stars, etc., etc. The primary thing that I want to get across here is we're going to focus on how do these motions actually observe what we see in the night sky. Of course, the two that have the most influence are the Earth's rotation and its revolution around the actual sun. Okay. Here's the first concept that we're going to address right now, which is kind of a review from the last lecture. You do realize that for the Earth to make one complete rotation, it takes 23 hours and 56 minutes. This right here, as you will see, is actually just the Earth spinning on its axis. Of course, this rotation is responsible for what we observe as day and night. Okay? The Earth actually revolves around the sun in 365.25 days. Again, just a review of these actual motions. And you notice that that point of the axis of our planet is a constant. Right now, it's always pointing towards Polaris. Now, to address another motion, this is what we're looking at here. And this is another motion that takes approximately 26,000 years to actually complete. This is called precession. Whenever you start talking about the Earth's precession, this is kind of the Earth's wobble, okay? So what's going to happen with this is the Earth, because we are, it has to deal with the physics of it all. What's going to happen here is that the Earth is kind of wobbling around in space just like this. And because of that, it's going to change what we observe of the night sky. Just know for now that that motion is actually called precession. Okay. Whenever you start looking at this, let's go ahead and address this first because it's one of the easiest ones to say how will it change the night sky. Well, the first thing that you can notice over here is right now, of course, our axis is lined up with the North Star, Polaris, and it stays in constant connection with that star. So it's almost a perfect alignment. It's not quite perfect, but it's almost perfect. Well, because of the Earth's precession, what's going to end up happening is our axis will eventually end up pointing towards the star Vega. And of course, this is going to change how we see constellations in the night sky. Okay, so whenever you start looking at that, approximately 11,000 years now, we're going to see that there's going to be a change to our night sky. Okay, because of this actual Earth's precession. Another thing that we actually have going on is you can see that our planet actually also changes its tilt. Of course, whenever you start changing the tilt here, one of the biggest effects that you will see is it's going to have an impact on our climate. Okay, what's going to end up happening as depicted over here in these images, right now this is the current situation. These are our conditions now. Notice that this is pointing towards Polaris, and then what's going to end up happening is in about 11,000 years, because of this change in axial tilt, notice that we're going to be pointed this way and pointed this way. Well, of course, you do have to take into account that this time of year in the winter, we are closer to the sun. So whenever we start tilting towards, we're changing the direct sunlight and we're actually closer. That's going to have a major impact on northern hemisphere temperatures. Whereas as you get over here, we have actually moved farther away from the sun in January. And what's going to end up happening now is we're going to be tilted back. Okay, and lower sun angles is going to result in much more extreme winters. So one of the primary things that you can look at is whenever this axial tilt changes, it's going to change the intensity of our actual seasons. Okay, so one of the first things you have to kind of understand is everything starts in astronomy with basic observations of the night sky. Okay, what we see now in the night sky is pretty much the same that our ancestors saw. So what it does is it gives us a good foundation from ancient astronomy to say what they saw then is kind of the same things that we're seeing now. And so we can use that data to further our knowledge of what's going on in the heavens. All right. First thing, let me go ahead and drag this down a little bit. I can see I'm blocking that out, so apologize for that. We'll just put this down here. Okay. First thing is whenever you start talking about constellations, constellations are nothing more than a gathering of stars that make out a shape. But these constellations do have a purpose in the night sky. As you can see, is they're blocking off regions of the night sky. So I like to think of constellations as kind of like a zip code, okay? What it is you look at Perseus, the constellation, and where it's located, it has its own little region of the night sky. Well, what we can do is we can use that as kind of a celestial locator, okay? Just like a zip code is an actual locator for a city and a state, constellations kind of act like state boundaries and state borders for the night sky, so that we can start to organize the way that the night sky appears to us, and we can use that to actually determine geographic directions, locations, etc., etc., etc. Okay. All right, so whenever you start looking at constellations, one of the first things you have to do is you have to be able to accurately identify. Now, of course, whenever most people look at this, the first thing they're going to say is this is the constellation, the Big Dipper. Well, here's the problem with that. The Big Dipper is actually not a constellation. The constellation's name is Ursa Major. The Big Dipper is something that is called an asterism. Now, what is an asterism? It's basically a group of stars that appear associated with each other, but are not. They're going to actually make out a shape. So you can see here that Ursa Major makes out a shape like a Big Dipper, like a big spoon, basically, what they call this ladle type of thing. Okay? Well, here's the thing about it. It's just very distinct in the night sky, so it's actually very easy to see, and that's why they call it the Big Dipper. But you can see as if you go through the entire constellation, you can see that there's actually so much more to it. So in other words, an asterism is just a small portion that makes out a shape of a much larger constellation. Okay, so that constellation that we looked at right there, that is actually Ursa Major. Okay, whenever you start talking about constellations, the best place to start, of course, are those on the Zodiac. These are the constellations that follow along the Earth's plane of revolution around the sun. So it's that flat area. These constellations are outside of that. So whenever you start talking about these, of course, where are these constellations most famous? They are most famous in the science of astrology. Now, here's something that I want you to realize is I'm an Aries, okay? So whenever you start looking at Aries and you start talking about your basic sign, what it is most people think that, oh, you're an Aries, so you probably saw the constellation Aries in the night sky. That is actually untrue. To determine your actual zodiac sign, it's when you were born, where the position of Earth was, and where the position of the sun is. So as you can see right here, where I'm highlighting with the mouse, that is actually where the location of April. This is our April orbit right here. So as you look, the sun is actually in the constellation Aries. So in all actuality, I'm an Aries, but I never saw the constellation Aries, and we'll never see the constellation Aries unless we have a major change in our orbit in the night sky, because of course it's in the daytime sky. Well, it's blocked out by the sun, so I can't see it. So the primary thing that I want you to know here is I want you to know that your sign is actually determined by the position of Earth and then the position of the sun. Whatever constellation the sun is in, that is your zodiac sign, and that's how that works. Now, of course, one of the big things, and I actually put this on our discussion board, it's talking about the constellation Ophiuchus. Okay, well, one of the primary things that have happened here is that because the Earth has actually changed its position a little bit, what it does is it has placed another constellation along right very near that actual plane, and that is, of course, the constellation Ophiuchus. Okay, so what we've done is just to keep it on a 12-month cycle of the year, we've kind of dropped it. But whenever you start adding it in there, you can start to make modifications to it and start to see that they are starting to change dates of the actual zodiac signs. So there's the extent of our astrology. Hope you enjoyed it. That's all we got for that. So now we're going to move on back to astronomy. All right, here's the thing that you want to look at. Again, I'll drag myself around here. I really need to fix my PowerPoint so that they're more conducive to this. Circumpolar constellations. Anytime you talk about a circumpolar constellations, these are constellations that, of course, rotate in a counterclockwise fashion around the star Polaris. Now, of course, why are they called circumpolar? Because they circle the pole. They circle Polaris. Now, one thing that you want to look at, and we're going to kind of try to explain here, is why does it do this? And why does it actually rotate counterclockwise? Well, that's kind of the whole thing that I want you to start to get, and we'll get that pretty much in the next lecture. I just want you to know about circumpolar constellations right now. Okay, some of the methods of the night sky, you can try this out, wherever you're at. What you can do is you, of course, can find the Little Dipper, or Ursa Minor, if you want the constellation, and you basically go and you find, of course, the star Polaris. Well, sometimes it's easy to find, but I will tell you, to accurately find Polaris, it is so much easier to actually go and find the Big Dipper. And at the end of the Big Dipper, you're going to have the stars Merak and Dubhe. Merak and Dubhe are referred to as the pointer stars. Well, the reason they're referred to as the pointer stars is because if you take and draw a line straight up, boom, they align perfectly with Polaris. Okay, so these are ways that you can navigate the night sky. You try to find Merak and Dubhe. Again, the reason being is that the Big Dipper is actually much easier to find than the Little Dipper, and sometimes it's really hard to just actually see. Another cool fact. Most people do not know that Polaris is actually a binary system. There are actually two stars there, Polaris A and Polaris B. Cool stuff when talking about that. Just fun little tidbit. Okay, there are other ways that you can find Polaris as well. You can go to Cassiopeia. And with Cassiopeia, you can actually go to the very center star of Cassiopeia and draw straight across, and voila, there you go. So this is just one method of actually finding Polaris, the North Star, in the night sky. And the reason you want to find Polaris is because you now know that you are automatically facing, as you can see here, you're automatically facing north. So it kind of sets a good, it's a foundation starting point of navigating the night sky. Okay, so with this, sometimes what you'll notice is you'll notice this bright band. You'll see all these constellations, but then you'll see this bright band of light going across. Well, that is actually the Milky Way. That's we're kind of inside the box looking outwards. So whenever you start to look at sky maps and such, and you start to see this area that is kind of highlighted, it's the part of the Milky Way that we can actually see, okay? Now, you can see in space, if you get out there in the darkness, you're going to see so many more stars. And the reason, of course, being is because you don't have light pollution blocking them out and everything. And it's much more difficult to actually try to put together some of these constellations. Okay, let me see here. One common misconception, this is just kind of a cool little tidbit, nothing huge about it, is because you're going to start to talk about what is called the celestial sphere model. Well, the celestial sphere is a big bubble around the Earth. So what it is it's like, think of you're on the inside of a balloon, and that balloon is the universe, and the stars are on those actual, that bubble or that balloon on the inside. Okay, so as you look out, the first thing you're going to do is like, oh, the stars are all the same distance because they're part of a constellation. That is actually inaccurate. Stars are not the same distance. You can see here, looking at the constellation Orion, you can see that the stars are like vast differences of how far away they are. We just take and put it into a two-dimensional model where we're like, okay, we've got this bubble surrounding us. There's that. But in reality, those stars are such vast distances away. It's just unfathomable. It's something that we just can't perceive. Okay. One thing that you guys can actually look at is this is actually a very important concept. Whenever you start talking about navigating the night sky, I told you that Polaris is a good place to start. Okay, well, the reason that Polaris is such a good place to start is because Polaris starts to say, wow, if we can see Polaris, we pretty much automatically know that we are in the northern hemisphere. So think of early navigation through the night sky, or excuse me, through the seas, and you're out on this open ocean, and then all of a sudden you're like, okay, which way am I going? Well, if you can find the star Polaris, you automatically say, if I'm heading towards that star, then I'm traveling north. Okay. Other things is because certain constellations are only observed at certain times of year. And so what the night sky acted like was kind of like a primitive calendar. Okay, so it indicated, because of course they didn't have cell phones, they didn't have the modern technologies we have, they didn't have calendars really, that said, here's the start of a new season, here's the start of the harvesting season, here's the start of the planting season. This is indicating what's going on. They use the night sky as kind of their calendar. Okay. All right. Here's what I want to talk to you about. This is that concept of the celestial sphere. This is a very large imaginary sphere. Again, it puts us into a concept that we can understand. You have to put it into dimensions that we can understand, and this is a two-dimensional image. So whenever you start talking about the celestial sphere, it's basically a way for us to understand that this is the navigation of the night sky. Okay, because here on Earth, what do? Of course, to get locations here on Earth, you actually use latitude and longitude. Well, what you start to look at is these early civilizations said, you know what? We need something to kind of set up locations of the night sky. And what they did is to make it nice and simple for understanding. They kind of reverse the way things really are. You've got what is called the geocentric model. So everything we perceive it because the Earth is stationary at the center and everything else is moving around. Of course, there were modifications to the geocentric model of the solar system, which we'll learn about later. But what you guys are going to, just to kind of understand the concept, this is what's going on, okay, with the geocentric model. Now, what's going to happen here in the 17th century is that we've actually started to say what is in reality is causing these motions. Well, we've transferred over to what is called the heliocentric model. Okay, with the heliocentric model, the sun is at the center and then everything else moves around it. And then in this case, the Earth is the actual moving object and the celestial sphere is the stationary object. Okay, so now you can start to see is what causes the constellations and everything move through the night sky? It's actually our rotation. Okay, what causes the changing constellations? Well, it's our revolution. So we'll be talking about that more in depth, and I'll do that in the next video where you guys can actually start to say, okay, here's how the night sky moves based on the Earth's motions. Okay. Whenever you start talking about this is the whole thing. We're not going to go very deep into this, but just realize that certain positions on the planet are transferred out into that celestial sphere model. So whenever you start talking about the celestial equator, you just take our equator and you project it outwards onto the celestial sphere. Whenever you start talking about the North Pole and you project it out, it's called the North Celestial Pole, the South Celestial Pole. But the primary thing that I want to get across here is that there's something called right ascension and declination. Now, I started to mention this and I kind of stopped previously, but how do you locate positions on Earth? You basically use the concept of latitude and longitude. Well, how do you determine the location of a star in the night sky? This is important whenever you're trying to program a telescope and you see people always punching in these numbers. Well, those numbers are the actual right ascension and declination numbers. Okay, so with that, here's what we're going to look at. We're going to look at some terms that basically describe where we are on the night sky. Let me go ahead and go back here. But right ascension and declination are huge because what this does is this actually tells us altitude off of the celestial equator, and then it tells us, in a sense, longitude. So right ascension and declination Our right ascension is equivalent to longitude, whereas declination is equivalent to the Earth's latitude. But it's on the celestial sphere. So now you're talking about I can actually have a pinpoint location and a number that goes with it for specific stars. Okay, here's some of the terms. Whenever you start talking about the meridian is that imaginary line that runs north to south. And the reason I'm doing it right now is because I'm actually facing north and south, or excuse me, I'm facing south. So of course, like this, okay? So you've got all this going on. That's the meridian. So whenever you say objects cross the meridian, it's actually kind of going to its highest point in the sky and then continuing on, okay? Anytime you start talking about the zenith would be straight overhead. Let's go into the next thing here. Azimuth angles. You have some telescopes that have azimuth angles, and whenever, I'm going to try to schedule a night where if you're in Springfield, you can come out and you'll actually start to look at azimuth angles. It's on the telescope, and you can set it up to actually move to these specific angles. Okay, so certain objects have certain azimuth angles. Okay, so whenever you start talking about all this, this is that celestial sphere model. How do we locate objects? Well, we locate objects using right ascension and declination. As depicted here, you can actually see that that star has a certain altitude. Okay, this one's almost at that person's zenith, the point directly overhead. But here's the thing. What is its actual real declination? And so whenever you start looking at that, it's kind of a neat little concept. What is its declination? And then where is it located on the celestial sphere? So it has a number. Okay. Another term. See it here. Sorry. This is the actual plane of the ecliptic. This is just the orbital path of the planets along. So whenever you start talking about the ecliptic, you're going to see that right there is the plane of the ecliptic. It's the path of the planets around the sun. So it's kind of putting everything on the same plane. That's the ecliptic. So that's just a term that you'll commonly hear. Why is it such a big deal? Well, whenever we get to come out at night and you guys start to see things in the night sky, I'll actually get you out there at dusk, because the reason I like to get people out there at dusk is because what it does is wherever you see that setting sun, so you'll see the setting sun, and what's nice is you can kind of trace a path across the sky, and it'll help you locate where the plane of the ecliptic is. And then because of that, you can then say, okay, this is where I'm going to go look for these planets. So it's a really good place. You can see the ecliptic there, and the planets are very near that ecliptic. Okay, so that's basically all it is. It's kind of like a navigating thing. All right. And there you can see the plane of the ecliptic, and what does it line up with? It lines up with those constellations of the Zodiac, so that's why we see them. So kind of neat there. The thing is about right ascension. Right ascension, whenever you start looking at it, it's based off of the vernal equinoctial point. So in other words, that right there, if you had a longitude of 0, then that is the equivalent of the longitude of 0. Okay, so this is like on Earth, it's Greenwich, England. That's the 0 point. So right there, where it's the vernal equinox, it's basically, that's the 0 point. So that's hour 00. I think I covered that here. Okay, there we go. Here's where it starts. This is how the whole thing starts. You start locking, excuse me, I'm getting a little erratic here. This is how we locate objects. So if you were to look at position A, right there, position A has a latitude of 20 degrees north, longitude of 120 degrees west. Okay, so if you were to describe that, you would describe it as 20 degrees north, 120 west. How do we do it? Latitude first, longitude. Whenever you start talking about the celestial equator, you do it backwards, or excuse me, whenever you start talking about celestial objects in the sky, you're going to say, here's a star, and that is the declination. And then, of course, you have the right ascension. So what you'll say is you'll be like, okay, instead of doing declination first, which would be equivalent to latitude, You do it right ascension, declination. Here's the thing about right ascension. Right ascension is in hours. I think the next slide here. Okay, so whenever you start looking at it, here's a good example of right ascension and declination. You're going to say it's 16 hours and 15 minutes and 20 seconds. So from the vernal equinox, so you go 15 hours and 16 hours and 15 minutes and 20 seconds. And then off of the actual equatorial plane, it's 30 degrees. So that's how you basically set it up. So if you're looking at something like this, this is how you determine of the circled star. The right ascension is 0 hours and 1 minute, and its declination is right around 30 degrees. Okay, so this is important whenever you start dropping the numbers into telescopes and everything, knowing it's right ascension and declination. Not a big deal. You won't be, we're not doing any activities on right ascension and declination. Just know that it is the equivalence of locating specific stars in the night sky to latitude and longitude, locating cities on Earth. It's kind of like, how do we find objects in the sky? So we've made a sky map. Okay. Here's the other thing, actual size. You can use angular distances. We'll move on from this. These are just ways that we can navigate the night sky. You can use your hands there to say, well, if you know that they're going to, like Saturn and Jupiter tonight are going to have 25 degrees of separation. Well, you can basically hold your hand up and say, okay, there's Jupiter. I know that for sure. Oh, wow, there's Saturn. Okay, so it's one of those ways that you can actually use angular separation between objects to determine what some of those objects are. Again, not that big of a deal. Here you can see some of the hand signals that we use. Pinky is 1 degree, 5 degrees, 10 degrees, 15, etc., etc., etc. So just an easy way to navigate the night sky. This is of the utmost importance. Pay attention to this. Here's the thing. Springfield, Missouri. We are located at 37 degrees north latitude. 2 ways to find the star Polaris. A, find the Big Dipper, go to Merak and Dubhe. Boom, it'll point right to Polaris. Here is another way that you can actually confirm that you have Polaris by looking at the altitude of Polaris off the horizon. So you'll go to the horizon, and what's really cool about this is you go to the horizon, Springfield is at 37 degrees north, boom, Polaris will be 37 degrees off the horizon. You go to New York City. New York City has a latitude of 41 degrees north. Polaris is 41. You go to the North Pole. The North Pole has a latitude of 90 degrees. What does that mean? 90 degrees. Polaris is at your zenith. So as you walk north, in all essence, what happens to the altitude of Polaris? It gets higher. Okay? That's an indication of a curved surface. We're walking on a curved surface, so Polaris actually is going to get higher in the sky. It changes our observations of the night sky based on where you're at. So where you are located determines what you are going to see. If you go to the equator and you try to find Polaris, good luck, because it's going to be right along the horizon. Why? The equator has a value of 0. It's actually a latitude of 0. So where is Polaris going to be? Right along that horizon. It's going to have an altitude of 0. Of course, you go to the southern hemisphere. What happens to Polaris? Not there. Okay. There's what you're actually looking at. You can use different types of tools to find that altitude, but I will tell you every single one of them will match up with your actual latitude as long as you are in the northern hemisphere. Okay? All right, so that concludes this first lecture. I've provided for you a video. That link, you can click that link there on the PowerPoint if you want. It's not required. It's just like a little extra thing that says, wow, that's some interesting stuff about constellations. Okay, sorry for this one being a little bit long. We got some of the basic stuff covered there. Focus on the motions and focus on how do we find Polaris and stuff like that. Okay, all right.